Welcome everyone to this another exciting video. Okay, we have 2023 August paper that was written by GCE candidates. Okay, so before we get started, I want to thank everyone for subscribing to the channel and sharing the channel link to others. Please, thank you. Continue subscribing as I'll be making some more videos. Okay, let's get started. So we have question B1. B1, Elena carried out an experiment and obtained the following results as shown. Where necessary, take the density of water as 1 gram per centimeter cubic. Okay, so the examiner gave out these initials. Okay, so they gave out the mass of the bottle to be 8 grams, and then the mass of the bottle full of water was 20 grams, and then the mass of the bottle of liquid X was 25 grams. So this was a non-liquid. Okay, and then the question A went on to state, name the instrument that can be used to obtain the results of mass. So if we look at mass can be measured using the beam balance scale. Okay, so to measure mass we use the beam balance scale. Okay, so the beam balance scale is used to measure the mass of the substance. Okay, and then in the second question we are told to calculate the volume of the bottle. So we are told to calculate the volume of the bottle. So now in here we have these initials. So these initials will be useful as we will calculate the volume of the bottle. Now we have to know that in the volume of the bottle that we are given, okay, the volume of the bottle that we are told to calculate was the bottle in which water occupied. So the water occupied the bottle in full. So if the water occupied the bottle in full, meaning that that volume which the water occupied is the volume that we are to calculate. Okay, so to calculate that volume, we can collect the data. Okay, so let's collect the data from here. So I'll put up the data from here and then I'll be doing some sketches. Okay, so you just allow me to do some sketches of exactly what was needed. Okay, so in there we have the mass. We start with the mass. So the mass, okay, we will assume the mass of the liquid. The mass of the liquid that occupied the bottle was 20. Was unknown, because this mass here which we have, it is the mass that was a combination of the liquid as well as the bottle. So the liquid plus the bottle, okay, made the mass of 20 grams. Okay, that was the mass which the liquid and the bottle made. Okay, so now we are interested in finding the mass of the liquid. So to find the mass of the liquid, what we do, we subtract. Okay, we subtract the mass of the bottle. Okay, we say 20, the mass of the total, 20 grams mass of the total, and then minus the mass of the bottle, okay, which is 8 grams. Okay, so when we subtract the two, okay, when we subtract 20 minus 8 grams, what we have is 12. We'll get 12 grams. So this was 12 grams was of the liquid. Okay, this was of the liquid. So the liquid had the mass of 12 grams. Okay, and then now we look at the actual density. So what was the density of the liquid? Because for the density by the examiner, we are given where necessary, takes the density of the liquid to be 1 gram per centimeter cubic. So density is 1 gram per centimeter cubic. Okay, so that is the density of the liquid. Now to make calculations in solutions, okay, in solutions we use the formula for calculating density, as density is equal to mass over volume. Okay, so if you may like this formula, you can make the volume to be the subject of a formula. So as you are making the volume to be a subject of a formula, you use this triangle. Okay, so this triangle is useful for making volume as a subject of a formula. Okay, I hope you're able to remember where we put a palm. When you put your hand on the particular item which you want to get, you have the actual item as a subject of the formula. Like for example, we have mass, which is a numerator there is on top. Then here we have volume, and then here we have density. Okay, we have D. Let me use D. Okay, so if we want to get our volume, so we put volume, we put our palm on volume, and then what we have is mass over density. Okay, that's what we do. So you can use this, but if you are not much okay with this, you can just use the formula direct. As you place numbers or values in there, the subject of formula will come forth as volume. Okay, so I'll place the values in the formula direct so that we will see exactly the volume which is coming out. So let's try to find the volume. So we state density given, which is 1 gram per centimeter cubic, okay, is equal to the actual mass. The mass which we're having is 12 grams, okay, and then over volume which is unknown, okay. And then from here what we do, we balance with the 1, and then we cross multiply. So when we say volume times the 1 gram per centimeter cubic, what you have is volume, we have volume, and then we have 1 gram per centimeter cubic. Oh, let me try to make a correction here. So we have 1 gram per centimeter cubic, and then V. Okay, that's what we have, and then equal to this other side. When we say 12 grams times 1, you get 12 grams. And then we divide all side by 1 gram per centimeter cubic. So this side by 1 gram per centimeter cubic, and then 1 gram per centimeter cubic. Okay, so when we divide this 1 gram per centimeter cubic into that one, what we get is volume. So we get our volume to be equal to 12 divided by 1. Okay, you get 12. Okay, so gram and gram will cancel. What will remain with is 12 centimeter cubic. So our 12 centimeter cubic is our answer. Okay, so this is the volume of the bottle. So this volume is for the liquid. The same liquid is the one that occupied the empty bottle. Okay, so the same liquid is the one that occupied the empty bottle in this form. So if this was the bottle, okay, and then there was the liquid that was placed inside of it. So this liquid was having the volume of 12 centimeter cubic. So it was full. So if the bottle is full, then the volume is this same value. Okay, so that is our answer there. Okay, then we move on to the other question. In the second question, we are told to calculate the density of liquid X. So liquid X is another liquid which we are given, okay, having its initial of mass to be 25 grams. Now this 25 grams, it's a combination. It's a combination of the bottle, the empty bottle. So take note that the empty bottle is having the mass of 8 grams. Okay, so the empty bottle is having the mass of 8 grams. So this one is having the mass of 8 grams. And then when it is full of the liquid, okay, when it is full of the liquid, okay, the actual mass which it is having is 25 grams. Okay, now how do we get the volume, the particular mass? How do we get the mass of the liquid which is inside there? So to get the mass there, we subtract. Okay, we take off the bottle since we are finding the density of the liquid. So in data correction, okay, in data correction there we state mass. We start with mass. Mass will be equal to 25 grams. Okay, let me try to write 25. So we have 25 grams minus 8 grams, okay, which will give us 17. So we have 17 grams as the mass. And then we look at the actual volume. What is the volume of the particular bottle? So the same bottle which we are given, the same bottle had the volume of 12 centimeter cubic. So remember from the previous part here, we had the volume of 12 centimeter cubic. So this same volume, we'll use it because the same bottles are used to measure the density of another liquid. Okay, so we say volume is 12 centimeter cubic. Okay, and then density, we don't know it. Our density is not known. So we place this in solutions. In solutions, we state density is equal to mass over volume. Okay, and then we can set up the values in the formula. Where we can say density given is unknown. Okay, let me write from here where density given is unknown, and then we look at the actual volume. So our mass is 17 grams, and then our volume is 12 centimeter cubic. Okay, so that is our actual volume. And then from here, what we can do, we can divide. Okay, so we can say 17 divided by 12. When we say 17 divided by 12, what we'll get is 1.4. Okay, so we'll get 1.4 grams per centimeter cubic. As we combine this gram and that centimeter cubic, we have 1.4 grams per centimeter cubic. Okay, so that's what you have. Okay, so that's the answer that we are obtaining. Okay, so we have 1.4 grams per centimeter cubic. And then moving on. Okay, before we move on, let me write this properly. So we have density is equal to 1.4 gram per centimeter cubic. Okay, so therefore now we can move on. Okay, so moving on, we have the question on stability. Okay, so if we can remember also in grade 10, there we have stability. Okay, and then we have center of mass, moments of forces, and so forth. Okay, so the question went on to state B2, figure B2.1 shows the same cone being placed at different positions, okay, X, Y, and Z on the flat surface. Okay, so now if you can remember very well, in grade 10 we had the different types of equilibriums. We learned about equilibriums. We learned about this one. For example, here we have unstable. Okay, unstable equilibrium. We have this one, we have neutral. Okay, if you can remember that well. And then also here we have stable equilibrium. Okay, so we have these types of equilibriums. So now if we see for the first one, which is X, we are given X, a tip of the cone resting on the surface. So this is the tip of the cone resting on the surface. So when the particular cone is resting on the surface, its mass is on top, and then the base area is less. Okay, so this cone is unstable. And then we have this one. This one is neutral because it can rotate to any side. So the cone lying on the surface is a neutral equilibrium. This one, just the same as the ball. So when the ball is resting on the surface, it is also said to be neutral. Okay, so we look at this other one. So the other one, it has its base area bigger. Okay, and then also lying on a huge area. So this particular cone, it is stable. Okay, so the base of the cone is resting on the surface, so it's a stable cone. Okay, now we have the question. The first question was defining center of mass. So when you're defining a center of mass, we can state it is the position on an object. Okay, object where the mass seems okay to act. Okay, or where we can say where the mass is considerably to be. We can say that, or we can say seems to act. Okay, so they say the position of an object where the mass seems to act, we call that as a center of mass. So this idea can be seen if you can remember the laminae. Okay, just to give you a picture of the laminae, if you remember, when we have something like this, and then from there they ask you which position is the center of mass. So we have that one as a center of mass. So this point is where the mass seems to act. Okay, So that particular point, okay, so we call that as a center of mass. So even in the given shapes, the center of mass goes on with many factors. So look at those factors. Okay, now in B, okay, identify the cone in a neutral equilibrium position. So the cone in a neutral equilibrium position is Y. So you can say cone Y. Cone Y is in a neutral position. Okay, so we can say cone Y. Okay, cone Y is the one which is in the neutral position. Okay, yes. And then we are given this question: state two factors that affect stability of an object. So there are factors that can affect the stability of an object. Okay, so one, we can have base area. Let's say base area. Okay, so when you have a smaller base, like in here, this object cannot balance properly. The base is so small, it will top over because the mass is focused on top there. So when the mass is on top here, and then the particular point where the cone is resting is it's of less base area, then this object can top over. Okay, because it will be unstable. But this one is bigger because the base area is big. So when the base area is big, then the object will be stable. Okay, so we can state base area is one of the factor, and then also the other factor is we can have center of mass. Center of mass. Okay, where exactly is the mass? So if the mass is on top, like for example here, the mass is more concentrated on top than the base, then this will have an effect on the stability of an object. That's why in odd times the vehicles were not stable. If you look at old vehicles which used to pack the luggage on top, those vehicles were not stable. Out of the mass was more centered on top than the base. So those vehicles used to top over as they were making sharp corners. Okay, so when stating, we have center of mass, and then the other one that we can state, the other particular reason that we can give is we can also give the height and the width of an object. Okay, so we have the width of an object, how wide is an object. Okay, yes, so and width of an object. Okay, so if the object in terms of the dimension, like for example, if the object is like this, okay, if you have two objects, let's say one object is like this, and then the other one is like this, and then this one will become more stable, this one will be stable than this. So width is important, then also height is important. So an object that is short, it is more stable than the one which is tall, or having the same base area. This one will become stable, this one will become unstable. So these two factors can affect the stability of an object. Okay, so moving on, we look at this question. Okay, this question is coming from balanced forces and balanced forces, and then we have drag, and then upward forces, and so forth. Okay, so we have the question on forces, B3. Figure B3 shows the direction of four forces acting on a car whose weight is 8,000 newtons. So the weight of the car is 8,000 newtons as it travels in the horizontal straight line. Okay, so this is our actual car that is moving in the actual horizontal surface. Okay, now we have to know some forces which are acting on this object horizontally. So horizontally there are two forces. Okay, we have this side where we have for example air resistance. Okay, so we have air resistance, okay, resistance, air resistance, and friction. Okay, so let me try to indicate properly. So we have air resistance and friction. So we have air resistance and friction, okay, plus friction. So these particular forces are the ones that are acting on D. because the particular object, the car, will face air resistance as it is trying to make a drag. Okay, because for this side we have a dragging force, so here we have dragging force, dragging force made by an engine. Okay, so the dragging force is made by an engine. Okay, so when the engine, for example, is running, this object will be made to be pushed forward, and then to this side we have air resistance. So the air that is blowing on this vehicle, they are pulling the object backwards. Okay, they are making the object not to move forward. Okay, so air resistance and friction are the horizontal forces that are acting on this object. And then we have the vertical forces. So we have the downward force, which is weight. Here we have weight, and then this side we have the lifting force upwards, the upward force there. Okay, so the upward force, you can say upward force. Okay, the upward force, or sometimes the lifting force. Okay, or we can say normal force. Okay, so these forces basically they are acting on an object. So this one is the upward one, and then we have the weight. Weight is the downward force. Okay, so weight is accompanied with gravity. Okay, so the weight of an object that was given, this force was 8,000 newtons. So it was also acting on an object. So these were forces which are present. So we have air resistance and friction horizontal with dragging force of an engine, and then we have an upward force, sometimes the normal force, okay, which is the opposing gravity, okay, as the object was moving. Okay, so the first question was the question was which of the two forces should be equal for the car? Okay, which two forces should be equal for the car to move at a constant velocity? Okay, so the forces that have to be equal, we have force B, and then also force D. So you can say force B, and force D. Okay, these forces have to be equal for the car to move at a constant velocity. So if this force is increased, the car basically, the velocity will increase. Okay, the velocity won't be constant, it will increase. Okay, so for the forces to make constant velocity, these ones, they have to be equal. Okay, so let's look at the other question that is the present. Okay, so the other question that is present, we are given. Okay, let me take it up to this part. So we are given B. Okay, we are given B. On B there, the question was the following table shows the sizes the sizes of forces acting on the same car after it had covered a certain distance. Okay, so these were the sizes of forces. So we have force A, it was 800 newtons, and then force B, it was 1000 newtons, and then force C was 8000 newtons, and then force D was 600 newtons. Okay, so if we look at these forces, they were now given with these values. So this table is showing the forces. Okay, where force C we are given to be 8000 newtons, and then we have force B, which is the dragging force. This force now we are given the size of 1000. Okay, 1000 newtons for force B. Okay, and then the other force, which is D, which is 600 newtons. Okay, we are given these forces, and then the upward one, which was the A, we are given 800 newtons. Okay, this one we are given 800 newtons. Now we are told to calculate, for example, in the first part we are told to calculate the mass of the car. How do we calculate the mass of the car? So take note that we are only given forces. So these forces which we are given, they are a composite of mass and gravity. Okay, they have mass and gravity. So we are told even to take mass, we are told to take gravity as 10 newtons per kg. So we'll use the formula of weight is equal to mass times gravity. Okay, where the mass given, if we look at the mass given, where we are not given the mass to say, and then gravity given is 10 newtons, and then we look at the weight given is 8,000. okay, so we're given the weight of 8,000 newtons. Okay, so this data we will try to plug it in the formula, and then we get the mass. So to get that mass, we apply where there is the 8,000, or where there is weight W, we place our 8,000 there, 8,000 newtons, and then equal to the mass is unknown, we say M, and then times the gravitational field, which is 10 newtons per kg. Okay, so we are told to take gravity as 10 newtons per kg, so we place our 10 newtons per kg over here. Now what we do, we divide all side by 10 newtons per kg. So this side by 10 newtons per kg, and then also this side by 10 newtons per kg. Okay, so when we say 10 newtons per kg into 10 newtons per kg, what we have is 1. Okay, 1 times M, will have our M. So our M will be equal to, when we state newtons and newtons will cancel, then we say, when we say 80 divided by 10, okay, so what to 8,000, to say 8,000 divided by 10, what we get is 800. So 800 kgs is what we have. So our actual mass, which we have mass will be equal to 800 kgs. So that will be our mass. Okay, then we can move on to the other question. So we are told to calculate the resultant force of the car. Now what is most important for you to take note of? Okay, I'll give the picture of resultant force, what it is. Okay, so when you have two forces, for example in here, this one and that one. Okay, so this side of the force, like in our case here, the car is having the force which is D. This side is pulling, then also this side is pulling forward. Okay, so these forces, they will be more in toggle. Okay, so when they are in toggle, what to have, when one force becomes greater, then it will pull the other force. So our force, which are horizontal, we have 600. Okay, and then to the other side we have 1,000. Okay, so now if this force, for example, is greater, if we have this one as a greater force, this force will pull the other force, this other side of the force. Okay, and therefore we will state resultant force, okay, or net force. Okay, so we'll say resultant force there. Our resultant force will be force, okay, will be equal to 1,000 minus 600. Okay, and then what we'll get as the resultant force, it will get 400 newtons will be our resultant force. Okay, so this one will be our resultant force, so we can say our resultant force is 400 newtons. Okay, so we look at the other question, the last one. So we have acceleration of the car. So when you are calculating acceleration, we use the formula. Okay, if we can remember, we use the formula for acceleration. So in here we have force, and then there we have mass, and then we have acceleration. Okay, yes, so we have this. Okay, so we have that. So when we are stating force is the product of mass times acceleration. Let me try to take it up. So when we are stating force is the product of mass times acceleration. Okay, so if we place these values in the formula like this, we have our mass here and then our acceleration there, and then this side is force, okay, in the triangle. So we are looking for acceleration. So our acceleration will be, acceleration is equal to force over mass. Okay, so this is our derived formula. Okay, or if you feel like, you can use this one, because you shouldn't struggle to make a triangle and then you come up with a formula. You make the subject a formula, but that is the time taking also when you're in an exam, but it's right. But please, out of time, you might save your time by using the formula direct. Force is equal to mass times acceleration, and then as you place the values you work out, then you have the subject formula. Okay, but I've made the subject a formula of acceleration in advance, okay? So we now see what we are given. Now, when you're calculating acceleration, okay, we have to take note of what resultant force is. So we use resultant force, okay, when you're calculating the acceleration of the car, because the resultant force is the force that has made an object to move to a specified direction. So if you have the two forces like this, okay, the actual force that becomes greater is the force that makes a drag. It will pull the other side and acceleration will be present, okay? There will be acceleration. So if we see 400 newtons was the size of the force that made the object to start moving, okay? Because if we look at the forces, when you have for example 600 here and then 600 here, the forces are balanced, and then here you add the total of 400 newtons. These 400 newtons which you are adding, it is a resultant force. It is the one that will cause the acceleration of this object, okay? And this same resultant force is what we use to calculate acceleration, because it is bringing about motion, okay? So to set up the values in calculations, we can place our place our force. We can correct the data by setting, okay, our force, our resultant force. Our resultant force will be equal to 400 newtons, and then we look at our mass, the mass of the car. The mass of the car, we found it to be 800, okay, it's 800 kgs, and then we can set up, okay, we can set up these values in the formula for acceleration. We can state in solutions, okay, we can state acceleration is equal to the force, which is the 400 newtons, and then divide by our mass, which is the 800 kgs, okay? So as we divide, we have our acceleration, okay, our acceleration to be 0.5, okay? So have our acceleration to be 0.5 meters per second, okay? So that's what we have, okay? Yes. So we can move on to the other question, okay? So the other question that we are having, okay, we have the question on okay, so let's try to see on the other question. So the other question that we're having, okay, we have the question on the simple machine, okay? So I'll take up this other question from the simple machine part, okay? So we look at this question. So we have B4, okay? So figure B4.1 shows a crane at a construction site raising a steel block of mass 100 kgs, okay? Through the vertical height of 16 meters in 20 seconds. So this question is coming on the machines. So if you look at simple machines, we have simple machines that can be used to lift up heavy objects, having their efficiencies, okay, and then also having their input powers, okay? So if we see from here, the input power of this simple machine was given to be 1000 watts, okay? And then this side is the block is weighing 100 kgs, okay? Yes, and then the vertical height, we are given 16, okay? And then the time taken, we are given 20 seconds. So we go on to calculate, okay, calculate the work done. So if we can remember, work done for an object that is rising up, okay, work done of an object that is rising up. If we look at the block was rising from the ground going upwards, where vertical height was given. So as this block is rising, there is gravity that is experienced, okay? So gravity which is experienced is taken as 10 newtons per kg, okay? So there is gravity which is experienced, so I'll write G is equal to 10 newtons per kg. Okay, so that is the gravity experienced for the block as it is rising up. So therefore, when you are calculating work done, you say work done is the product of mass times gravity times height. Okay. okay, for this block was rising upwards. So we can apply the values in here. Okay, we see what we are given. So I'll do the data correction. Okay, so in data correction there we have mass. The mass of the block is 1000. Okay, so you can place our 1000 kgs from here. Okay, 1000 kgs. Okay, and then times the gravity. Gravity is 10 newtons. Okay, and then times the height which the object was moving to was 16 meters. Okay, so 16 meters was the height. Okay, and then from there now we can go on to multiply the values. So when we multiply the values, what we'll get, okay, we'll get 1000, we'll get 16,000. So 16,000 is what we'll get. Okay, so we'll have 16,000 joules. So take note that work done is measured in joules. Okay, so this is what we are getting. Okay, then we move on to the other question. So let me write from here. We have 16,000 joules. So that's what we have. And then the second question we are given power developed by the crane. So when you are calculating for power, okay, so power is given as work done over time taken. Okay, over time taken. So that's the formula for calculating work power. Okay, so we see exactly what we are given in terms of data. Okay, so in data correction we see what we are given for work done. So our work done given, we are given work done, the one which we have found the 16,000 joules as our work done. And then we look at our time taken. So time given from the question we are given 20 seconds. Okay, so the time given is 20 seconds. So our time given is 20 seconds. Okay, yes, so we can place this data in the formula and then we get the solutions. Okay, so in solutions we can state power would be equal to work done. Our work done is 1600, or let me say 16,000 joules, divide by 20 seconds. Okay, so as we divide 20 into 1600, okay, what we'll get afterwards, power will be equal to 800 watts. Okay, so get 800 watts. So that's what we have. Okay, so we can move on to the other question. So the other question we are given on B, given that the power input of the motor is 1000. Okay, 1000 watts, calculate the efficiency of the crane. Now what I usually recommend on this part, when you are using the formulas for calculating power input, or let me say when you're calculating the efficiency of the crane, take note that this is a motor. Okay, so the efficiency of the motor can be given as energy input over energy output and then times 100. Okay, so that's the formula that you can use. Or if you don't want to use this formula, you can use the power, or let me just state efficiency is equal to power output over power input. Okay, you can say power output, okay, power output over power input. Okay, so we can use this formula. Okay, so it gives out the same answer. Okay, so this one or this one, whichever of the two. Okay, so if you may like, we may test the two, because there are two ways of doing things. Okay, but I prefer using this one, which is the efficiency is equal to energy input over energy output and then times 100. Okay, so for this formula, what we do, we first of all look at what we are given. Okay, we look at the data. So in data correction, okay, we will see first of all our energy input. Okay, so if you are using this formula, so you look at the energy input. Now energy input is energy input is the potential energy, or work done due to gravity. So work done due to gravity is the energy input, because that energy is the energy which the machine puts in to perform the work. Okay, so our energy input in our case, we found work done due to gravity as 16,000, okay, joules. So our energy input, okay, our energy input is equal to 16,000 joules. Okay, and then what are we having as the energy output? So to get energy output, we use the formula. Okay, so energy output, okay, we use the formula which is energy is equal to power times time, okay, to get the energy output. So we use this formula, energy is equal to power times time. So where the power is the input power, we always use the input power when you're using this formula. Okay, so we say energy is equal to the power input we are given in 1000. Okay, so you say 1000 watts, 1000 watts times the time taken. The time taken in the question we are given in 20 seconds. Okay, so if we look at the time taken from the question, so we are given 20 seconds as the time taken. So we apply that time taken in the equation. So when we apply the time taken, when we multiply 1000 times 20, okay, so if we multiply 1000, okay, times 20, we are getting 20,000. Okay, we are getting 20,000 joules. Okay, so therefore for this actual formula you can apply the data. Okay, you can apply the data in the formula. You say efficiency will be equal to so in here you can say efficiency will be equal to okay, you can say efficiency is equal to energy input. So our energy input, if we see, we have 16,000, so you can say 16,000 and then over our energy output, which is 20,000, okay, and then times 100. Okay, so when we divide 16,000, okay, when we divide 16,000, okay, divide by 20,000, okay, what we'll get our energy to be, we'll get 0.8, and then 0.8 times 100, okay, what we'll have is 80%. So we'll yield 80%. So we'll get our efficiency to be 80%. Okay, so this is when you're using this formula, you get the efficiency to be 80%. And then also in the similar form, if you are using this one direct, this one is a direct formula, you can say efficiency is equal to the power output. So the our power output which we have, okay, so the actual, okay, so we can say the power output, the given output power is this one. Okay, we are given 800 watts. This is what the machine has given out. So we can say 800 watts. Okay, 800 watts divided by 1000, the input power. Okay, the input power, which is 1000. Okay, and then times 100. Okay, so take note that I'm getting the power output from this calculation. So the power developed by the crane is the power output. So this power output is 800 watts. Okay, so when you divide it over 1000, okay, what you have in the end, you have 0.8. When you divide this one and by this one, you get 0.8. Okay, so 0.8 times 100. Okay, what you have afterwards, okay, you have 80%. You're still getting 80%. Okay, so all the sides are the same. So when you use this method, you find the 80%. Even this method will give you 80%. So whichever of the two. Okay, so we have the two. Okay, so now from this part we can move on to the other question. Okay, so on the other question there we have the question on boiling, evaporation, and temperature. Okay, so question B5, the graph, the figure B5.1 is the graph showing the variation of temperature. Okay, temperature of Celsius in Celsius with the time in seconds when frozen water is heated for a period of time. So I hope guys were able to remember the heating curve. So we have what we call the heating curve. Okay, so now on the heating curve there, it is important to take note of the changes of states. Okay, so the change of states basically they should start up in this form. So if I can give a sketch of a heating curve, so we have these particular points. Okay, so here we have a solid. Okay, so a solid there, a solid, and then the change of state. The change of state is melting. Okay, and then here we have liquid ice, for example. Okay, so here, and then we have for example here boiling. When boiling begins, evaporation will occur also. Okay, so there are these actual points. So in here, when boiling is present, then we will have the change of state from liquid to gas, and the evaporation will take place also. Okay, now what is important for our case, we are given from A to B. So what is this actual change? Okay, so this change is melting. So here we have melting, and then on the other side also we can have boiling. Okay, so this is just the basic I'm giving, but before we look at the question. Okay, so the initial point of starting where the particular temperature was starting was 0. So the temperature was starting at 0, and then the maximum there is 100, and then when 100 reaches, and then the particular substance will change into a gas. So this point is boiling, and then here we have melting. Okay, so let's try to see the questions that are given. Okay, what physical change was happening to the water at the point labeled A? So at the point labeled A here, basically there was melting. Okay, melting was happening because this was the 0. So at this point the substance was purely ice, and then the substance began to change in state, okay, to form a liquid. Okay, because at this point we should have liquid ice. Okay, liquid to ice. So if there is liquid ice there, then the substance what made it to change into liquid ice is melting. So the actual change at A we can say melting. Okay, so there was melting. Okay, so we have B. In what state is the liquid at between point A and B? So between point A and B, okay, between A and B there we can say liquid, because at B there we can state to see, if we see from the parts, B there was 100 degrees Celsius. So take note of the temperature here. We have 100 degrees Celsius. Okay, so 100 degrees Celsius at B, it was purely liquid. So from this particular change from there to there, the substance basically was liquid, to say liquid. Okay, so the reason is of temperature. We have 100 degrees Celsius from here, so the substance was liquid at this particular point of temperature. Okay, but when it comes to the cooling curve, where temperature is not given, okay, where we are not given on the side here, we are not given the actual value of temperature, we can say liquid ice. But in our case here, the graph was had the 100 there, so meaning that the substance was liquid. Okay, so the substance here was liquid. Okay, and then let's try to see the other question. When the temperature starts to rise, the volume initially decreases and then increases. State a reason for this observation. So here we have the two things. When temperature at first, okay, when the substance basically is a solid, it's a solid like this, and then it begins to melt. Okay, it begins to melt. Then the volume will reduce. If it is a solid, it will have more occupation of the volume. And then when temperature begins to rise, the particular mass of the liquid will start increasing, and then the volume will reduce for this solid. Okay, so the solid will, the particular volume will reduce, and then the mass will increase. Okay, so mass will increase and then volume will reduce. Okay, and then afterwards, when you increase volume, when temperature is increased, when temperature is increased, what will happen is the particular liquid will start expanding. The liquid will start expanding. As it expands, then the volume will increase. Okay, so the liquid, when it is expanding, volume will increase. So it's just vice versa. Okay, so when you heat the liquid, when you heat ice, okay, volume will reduce, so that this particular ice changes into liquid. And then from there, when the liquid begins to heat again, when temperature continues to increase, then the liquid will start expanding. So we have that. So let's write the explanation from the parts. Okay, so in writing we can state when ice melts, okay, comma, okay, the density and mass will increase. Okay, will increase. Okay, while volume will reduce. Okay, and then steady and at steady increment of temperature, okay, comma, the volume of the liquid will increase due to expansion. Okay, so liquids basically they expand. So as they expand, basically the actual volume increases. Okay, so that's what we can state for this part. Okay, so let's move on.